Ultrasonic Measurement and Testing, a knowledge floater from Karl Deutsch Wuppertal with videos, animation and audio. Is the railroad used 1,000 times a day still safe, or could a hair fracture in a wheel rim spread and cause an accident? Has the pipeline been checked for cracks that might cause an environmental disaster? Wherever human or environmental safety is at risk, components are measured and checked ultrasonically. The method is similar to echo sounding. Sound pulses of high frequency are sent through the material and reflected back from every edge, crack or defect. The lower picture shows measurement of the thickness of a plastic tube wall. The transit time of a short ultrasonic pulse is measured. Combined with information about the speed of sound in the material, the wall thickness can be easily calculated. The speed of sound varies widely in different materials. In air, as everyone knows, sound travels at 330 meters per second. In water, sound travels more than 4 times as fast, at 1,500 meters per second. In steel, sound travels 4 times faster still, at 6,000 meters per second. Ultrasound is sound of such high frequency, more than 20 kHz, which means more than 20,000 oscillations per second, that it is no longer audible. Technically, ultrasound is produced by means of a vibrating crystal in an ultrasonic sensor, also called probe or transducer. Using the piezoelectric effect, electric pulses are converted into mechanical waves, in this case sound waves. The ultrasonic test equipment used for crack detection is called ultrasonic flaw detector and normally generates ultrasound with a frequency of several megahertz. In many cases, so-called longitudinal waves are used for crack detection. They form a push-pull sequence, causing rapid expansion and compression within the material as the waves pass through it. Because air is a poor conductor of ultrasonic waves, a film of water or oil is spread on the material to create direct contact with the ultrasonic sensor. In the picture, this film appears in green. The fluid is called coupling medium. Ultrasonic test equipment. The sensor emits a short ultrasonic pulse which passes through the component being tested and is reflected from the far end. The sensor acts first as a transmitter and then as a receiver. A test instrument not only produces the electrical impulse to set the crystal in motion, but also possesses a monitor screen that displays the ultrasonic signals as they travel through the material. The ultrasound pulses are periodically produced. The pulse repetition frequency is so high, around 1 kHz, that the operator sees a static image. As the pulse returns from the material, the sensor works as a receiver. The initial pulse and the reflection from the back wall are clearly seen on the screen. The total travel time corresponds to twice the length of the piece. This elegantly simple principle is called the impulse echo method. Wall thickness measurement. Ultrasound is perfect for measuring the thickness of pipe walls, as the transit time of the pulse is exactly 2 times the thickness of the wall. This particular type of measurement does not really require a monitor screen. All it needs is a digital display to show the reading. Ultrasonic measurement of the pipe wall thickness in petrochemical plants not only provides safety but also saves time and cost. For instance, pipes carrying hot or aggressive chemicals must be regularly checked for internal corrosion. A shutdown of the production would cause high costs. Nevertheless, ultrasound can be applied since only one side of the pipe must be accessible. Checking for internal defects. Ultrasonic reflections from internal cracks and pores arrive earlier than reflections from the back wall of the component. This phenomenon has been used for the detection and subsequent evaluation of internal defects. The illustration shows various types of defects and how they are displayed on the screen. In the absence of any defect, initial and backwall echo can be clearly seen. If the ultrasound is fully reflected by a defect, the echo returns earlier, but with undiminished strength. Figures 3 shows a defect close to the surface where the echo is repeated several times, but more weakly each time. At the edge of the defect, two echoes are visible, one from the defect and one from the back wall. The same holds for figure 5, where the defect is smaller. Weld inspection. Checking welds for defects is a demanding task, the high school of ultrasonic testing. Angle beam sensors are used to transmit sound waves obliquely into the material. Depending on the particular weld, thickness, distances involved, reflective conditions, etc., various types of defects can be detected at the bottom of the weld, for instance cracks or non-welded root. In the center and upper weld areas, lack of fusion is a common defect. The video on the right-hand side shows the movement of the ultrasonic sensor with respect to the weld. The ultrasonic sound path is marked on the front side of the workpiece. A defect signal is clearly visible. Automatic testing of pipes, bars and rails. Because of their length and the high throughput requirements, objects like pipes, bars and rails are often checked automatically. Testing machines detect and mark the defects, and the defective components are automatically rejected. On the left, an ultrasonic rail test is shown. Water jets carry the ultrasound from the sensor towards the rail and back. Pipes can be tested by means of a portal. While the pipe is rotating, the sensors are linearly moved along the pipe. The pipe is therefore scanned in a helical manner. Steel bars are fed by means of a roller conveyor into the ultrasonic test machine, here hidden behind gray splash protection sheets. Multiple sensors, in this example 9, check the entire cross-section of the bar as it passes through the machine. The customer is guaranteed a fault-free product.